Okay, welcome everybody. I'm glad you're here. I appreciate it. We are going to have about a 60 to 70 minute presentation tonight. I know this is scheduled for an hour and a half, but I want to leave some time at the end for questions. And we are going to go through supply chain network planning with Excel. I've got a couple of case studies to go over. I'm going to use the Excel solver, which I refer to as the original AI. If you're already familiar with the solver, maybe you haven't seen it used in the way we're going to use it tonight to optimize supply chains. I found this very effective and efficient over the course of my career. And I'm guessing that some of you may not even ever heard of the Excel solver, which is fine. We're going to go through a real brief introduction to that. But if you're in supply chain, even if you're just any kind of an analyst outside, inside of supply chain or outside, the solver is a really very, very sophisticated tool, and it would do you well to learn how to use it. I think you'll up your game. You'll increase the value to your organization if you're an employee, and if you're a consultant, it will increase your value to your clients and actually give you a broader range of clients that you can do work for. So having said that, let's jump right in. So what we're going to cover tonight. So I already talked about Excel solver. We're going to go through a brief introduction on that. And we've got two case studies that will be using the Excel solver in both of those case studies. The first one is a Greenfield analysis. And a Greenfield analysis is a design optimization. So we're trying to design a network. So what we're really trying to find in a Greenfield analysis is answer a question like, what's the best location for my warehouse, a production facility, distribution center, etc. And we're going to review a case study that I actually did, and it was for finding the best location for a distribution center for a 650 million annual revenue healthcare wholesaler. We'll then go into a case study where we'll do some network optimization. The difference between this case study and the first case study, in Greenfield analysis, we have no idea where the facility is going to be. We are trying to find, that's the objective of the Greenfield analysis, trying to find the location, the optimum location for my facility. In an operations analysis, network optimization, I've already got a network in place. So I've got production facilities, maybe. I maybe have some third-party contractors that make this product for me. I've got warehouses, distribution centers, etc. And what I'm trying to do now within this given network is use it the most effectively, right? So I want to be able to answer a question like, how much of each one of my products should be produced in which production facilities to flow through which distribution centers to go to which customers. So we're really trying to work within an existing supply chain and minimize the cost. The case study here is going to be from a $6 billion revenue soft drink manufacturer. I've changed some of the names and some of the data, but it's the same basic type of a problem that I've solved for clients in this space. But just to point out, today's objective is to get some familiarization with these tools. I don't expect that anybody over the course of a 60 or 70 minute webinar is going to be an expert in this, but hopefully it gives you an introduction to what Excel can do and spark some interest for you to seek some further training. Just a real quick background about myself so you know who you're listening to. My name is Ed Orlandi. I've got a background in aerospace engineering. I've got an undergrad in aerospace engineering, a master's degree in operations research, and I spent about 6 years designing military aircraft before I went back for my MBA. Coming out of MBA school, I worked for Deloitte Consulting, one of the big four, for about 8 years, which is where I kind of discovered supply chain and kind of fell in love with that. After Deloitte, I spent 2 years at a software company called i2 Technologies. They make software, supply chain planning software. After that, I spent about 12 years in various consulting firms, but always specializing in operations improvement in supply chain design and optimization. After that, I've spent about the last 10 or 11 years in corporate supply chain positions in companies like Dr. Pepper, Galderma, Thermi Aesthetic, and the most recent gig I had was I was head of supply chain for Biote Medical. I left there about 18 months ago and started my own small supply chain consulting operation and been doing that, which is where I've really kind of doubled down on what I'm going to show you tonight. I've really used the kinds of methods we're going to go through tonight. I've used predominantly over the last 18 months in my supply chain planning consulting firm. So I've been doing this kind of work since I left grad school in 1992. So I've got just about 32 years experience in supply chain. So quite a lot of breadth of stuff that I can dip into to try to help people. So let's go through an introduction to the Excel solver. As I mentioned, this is going to be the tool we're going to use throughout the training. So I've got a kind of a fake problem here I made up, and I think to save a little bit of time, rather than go through reading this, I am going to jump into a spreadsheet. I think that's going to help demonstrate a lot better than some words. So we are going to jump over to the spreadsheet, and okay, there we go. So this is basically, like I said, it's a made-up company, but just something that gives you some kind of an idea of how the solver works. So this particular company is called Modern Furniture. They make desks. In this particular case, they make two types of desks, a standard and a deluxe model. So we've got the information about these desks up on the top here. They sell this standard model for $1,450. They've got $825 worth of material cost into it. So they've got about a $5 profit for that. The deluxe model is a $3,600 sales price, $1,050 in materials. So the profit on there is $2,550. They've got two different types of labor required to produce these desks. They use carpentry and finishing. A standard desk uses 2 hours each of carpentry and finishing, and a deluxe desk uses 6 hours of carpentry and 14 hours of finishing. Gives you some kind of an idea maybe of why the deluxe desk is so much more pricey than the standard. It uses a lot more labor and materials to make that. Now, from our marketing department, we know that we can't sell any more per month than 1,000 of the standard and 300 of the deluxe. So we don't want to make any more of that. But the question here now is, given this information, what is my production plan? How many of each of these desks do I want to make if I want to optimize and maximize my profitability? So down here, we've got a model where we're going to be able to tweak some of these numbers and see if we can figure this out, right? So the two yellow cells are the variables that I have the ability to change, and that's the quantity of the desks. I can change the number of standard desks and the number of deluxe desks. So let me just pop a 1 into each one of these to show you how this model works. And you can see if I make one standard desk, I'm going to get $625 in profit, which follows from above. And I'm going to use 2 hours each of carpentry and finishing. One deluxe desk, I'm going to have $2,550 in profit. And like we pointed out above, 6 hours of carpentry, 14 hours of finishing. Then I've got my totals. I've made a total of 2 desks. I've got $3,175 in profit. I've used a total of 8 hours of carpentry and 16 hours of finishing. Now, we also know that based on the number of employees that I have, I've got a total of 1,900 carpentry hours and 2,400 finishing hours per month. That's it. Once I hit those numbers, I'm done for the month, unless I want to use overtime. And the company's already said they prefer to see what this looks like before they dip into any overtime. So the last column on the right here, our slack, tells us how many hours we've got left over. So based on what we've got in here right now, if I made one of each of these desks, I would have used a total of 8 carpentry hours, leaving me 1,892. I would have used a total of 16 finishing hours, leaving me 2,384. The goal here is to try to get as close to possible as using all of my resources. That's what's going to allow me to maximize my revenue, or my profit rather. So this cell E21, which is where my profit is, that's the one I'm trying to maximize. So what can I do here? Well, I can start just typing numbers in, right? What if we made 100 and 100? Okay, well, that's pretty good. I've got $317,000 of profit, but I've still got a ton of hours left. So I'm not quite there yet. What about 125 and 125? Better yet, but I still haven't hit it. 150, oops, 150 and 150. Well, now I've used up, you can see over here, my slack is 0 for finishing, meaning I've used 2,400 hours, which is exactly what I had. So if I were to make this combination, 150 of each desk, I'd be done for the month because I don't have any more finishing hours. I still have carpentry hours, but it does do me good to partially make a desk and not be able to finish it. So this is it's a feasible solution, but it's not an optimal solution. So I could continue trying to guess these numbers in these yellow cells and see if I can finally get to a point where I've maximized this or I can use this tool that we're going to show you how to use here in a minute. So to use the solver, you want to go up to the data tab up on top, all the way over to the right, underneath data analysis is called the solver. Now, if you're looking at your Excel and you don't have the solver there, it's no problem. Excel, the solver is an add-in, which means it's already in Excel, but you have to invoke it. And if you don't already see solver, here's what you need to do. Go all the way up to the top left-hand corner to File. You're going to hit File. You come all the way down on the bottom left to Options. You're going to want to hit Options. That's going to open up this other window here. The second from the bottom says add-ins. I'm going to click on add-ins. It's going to open up another window for me. At the very bottom here, under manage, you can see Excel add-ins. You want to make sure the Excel add-ins is what's checked. Hit the go box. And the very bottom here, you can see solver add-in. Mine already has the checkbox. We know that because I could see solver up in my window already. But if that's not already clicked, you want to click solver add-in and then click OK. And then the solver should be right up there in the upper right-hand corner. So we're going to click on solver. It's going to open up my management window for me. So let's go through this and try to understand what all these data elements are. So the first thing it's asking me at the very top is to set the objective. What is it we're trying to do here? If you recall, we are trying to maximize our profit. So this allows me to enter a cell here. It's already selected. E21 is what the total profit is for both of these desks. And I clicked in there already. And what is it? The next row says to do what? I want to maximize this. So I've got the maximize radio button clicked. I could minimize as another option. If this were some kind of a cost situation, I would want to minimize my cost. Very rarely, but sometimes you might want to drive this function to a particular value, in which case you'd click value of. But in this case, we want to hit maximize because we're trying to find the maximum profit. So now the next thing says, by changing what variables, what is it that is going to allow me to maximize this? This is asking, what have I got the ability to change here in this model in order to perform this optimization? So here you can see I've got a named range called prod underscore units. I'm going to close this window for a second and just come up here and show you. This is where all my named ranges are stored. Prod underbar units. If I click that, you can see it's highlighted the two yellow cells. So prod underscore units in my case simply means cells C20 and D20. So that's what it's telling the program, that you can change these two cells in yellow here, do anything you want to those within the limits we're going to talk about in a minute, but those are the two things you need to change in order to be able to make this work. So what constraints am I subject to? So the first one here says S22, or excuse me, it's E22 and E23 are less than F22 and F23. What this is telling me is the total number of hours that I've used need to be less than or equal to the total number of hours that I have, right? That makes sense. I can't use more than 1900 and 2400. And this is where you tell it what to do. I've just told it that these two cells need to be less than these two. And then I also know that the production units, my marketing department has said I can't make more than 1,000 of the, or I can't sell rather more than 1,000 of the one and 300 of the other. So I'm going to put that in there as my other constraint. So now, with the exception of one more thing, everything's set. So my solving method down here, I've got three options. The one we're going to talk about right now is simplex LP. LP simply stands for linear programming. What it means is all of the relationships between the variables in here are linear in nature. There's nothing squared. There's no, I don't have any sines or cosines or anything like that, which makes it a lot easier to solve this problem. Anytime you can use the simplex method and you have linear relationships between your variables, that's what you want to do, right? So I don't want to go into more detail than that right now, but we're going to use the simplex method. So we're going to come down here, we're going to click, excuse me, I'm trying to let somebody in, sorry. I'm going to hit solve, and it's already solved it. You can see here, I don't know where that other window went, but there it is. Okay. And It's found out that 762.5 and 62.5 is the optimum. And you can see down here, it figured out a way to use all of the hours available, right? When you've got no hours left, that's not always possible, but in this case, it figured it out. Now, some of you are looking at this going, okay, this doesn't make a lot of sense because I can't make a half a desk. And you're right. There is a way within the solver that I could force this solution into an integer solution, but it's significantly more difficult to solve an integer problem than a non-integer problem. Right now, we're using the simplex method. If I force this to use an integer problem, it's going to use something called branch and bound. It's outside the scope of this, but just know it's significantly more difficult. It's usually a lot easier to figure this out and then go, okay, I'm just going to drop this down to 760, 761, and 62, right? And now I'm within my bounds. That's the easiest way to do that. So right there, you can see how quickly and easily this solved that problem. Imagine, if you will, this is a super easy problem. It's only got two types of desks and two types of labor. Imagine if this company had, let's say, 12 different type of desks and 14 different types of labor and material constraints that they had. It would be extremely difficult to figure that out by hand. This, if we wanted to continue the process we started with by guessing on these two yellow cells, we probably would eventually have gotten to this. It would have taken some time, but imagine if we had that 12 different items and a ton of different resources. It would be next to impossible to do that by hand, or not without a lot of hours. So this makes it really just so much easier and just efficient to use this to solve these types of problems. And this is the file that or the type of solution we're going to use for the two case studies that we're going to do. So let me go back to our let's see, where is my, sorry, there we go. I'm going to come back over here. And now we're going to go to our Greenfield analysis case study. And let's take a look at this. Is from an actual client that actually had a distribution center in Fort Worth, Texas, down here. What this figure represents is all of the customers, and every dot is a customer, and the size of the dot represents the weight that each one of these customers received over a 12-month period. In a minute, when we go to the spreadsheet, I'm going to show you the data requirements to do this, but this is just kind of what it looks like visually. All these customers are in the continental United States, and you can see there's some big customers out on the West Coast. There's a couple big ones out here on the East Coast. We've got some up by Chicago. And this company, under the current Cincinnati, when I started to work with them, they had one distribution center in Fort Worth. You can see it's fairly far from some of their bigger customers. So there's two things going on here in the optimization. One, what we're trying to do is find a different location for the distribution center that will minimize my transportation costs. And two, try to get a little bit closer to my customers so I can increase my customer service. So we're going to go back over to our spreadsheet now and jump into this case study. So let's start by taking a quick look at what the data requirements are. There's really not a lot of data you need to do this. So on this spreadsheet shows everything that I needed and pulled down from the system in order to be able to do this optimization. First is just an index number, 1 through n of the number of customers. And then for each customer, what we've got is the number of shipments they had over the time period. In this case, it was 12 months, the weight, the name of the customer, which the name's not really important for the analysis, but it's just there for convenience sake. And then you've got where they located. So that's what I need to know. I need to know, where is this customer located? I need to know how much was shipped to them and how many different shipments did they have. So this first customer, which was a Costco depot in Miraloma, California, they had 113 shipments over this 12-month period for a total of just under 2 million pounds. In total, we had a total of 443 customers. We shipped 39 million pounds, and there was a total of 24,735 shipments. Okay, so that's the data you need. So what does the model look like in order to be able to do this kind of analysis? Well, it's not really that difficult. Here's the model right here, and you can see the first few columns are exactly the same. What I've done when we get to column F here is I've swapped out latitude and longitude from the address. I have to have latitude and longitude in order to be able to do a mathematical calculation to figure out a distance between 2 points. And there's plenty of ways to do this. I don't want to go into this, but you can either use Google Earth Pro. It's a little bit lengthy if you've got 442 different customers you have to go in there and get, but there's plenty of places where you can go in with a spreadsheet that looks something like this with addresses, and you'd come out with the latitude and longitude. So what are the additional things we need here? Well, up here in the green is the latitude and the longitude of the Fort Worth distribution center. The last two columns here, H and I, this 1166.2 is the distance in miles between this distribution center and this customer. And I don't know if you can see that very well. It's a fairly lengthy, it looks scary, but it's not really that bad. This is called the Haversine formula, and it's just some geometry, and it's finding the distance over a globe, over a curved linear surface. If you have 2 points on a curved surface, it tells you the distance between those 2 points, a straight line. It's called it's just a straight line distance between those 2 points. The other thing we've got here, I've multiplied the distance times the weight. Now, why do I need to do that? Well, let's think about it for just a minute. Let's think of an example of where I might have 2 customers. I've got one up in Seattle and I've got one down in Jacksonville, Florida. If those are my only 2 customers, I could probably draw a straight line between those 2 and pick a point right in the middle, and that's going to minimize my distance. Easy peasy. But what if I then told you that the Seattle customer got 99% of the shipments to them and the one in Florida only got 1%? Well, now I'd prefer to be right across the street from the Seattle because that's going to minimize my distance, right? So I really need to know 2 things. I need to know the weight and the distance. So if I multiply these 2 together, I'm basically weighting each one of the customers by the weight that they get, right? Somebody that gets 1.9 million pounds is going to be much more important than somebody that gets, 2,000 pounds. I'm going to want to be a lot closer to that 1.9 million pound guy than the 2,000 pound guy. So up at the top here, this 39 billion number, this is the sum total of all the distances and the weights. This is the number that I am going to want to minimize in my optimization. Okay, so what this tells me is off the bat, in order to do this 12 months of deliveries, there were 24,730 shipments, and it was 22.8 million miles were traveled to do that. Okay. The other thing that I want to point out over here, there's a couple of price sensitivity statistics. If I travel 22.8 million miles over 24,730 shipments, each shipment on average was 923 miles. The more important number is on the bottom. What this tells me is each pound went an average of 997 miles. This number here is going to give me an indication of the cost of this scenario, right? When I'm doing either full shipments or LTL, less than truckload shipments, there's 2 things that matter the most. It's how much it weighs and how far I've got to go. And this thing takes both of those into consideration, is telling me that each pound on average went 997 miles, right? So the baseline here, 22.8 million miles, each pound went 997 miles. There's some statistics over here that we can use for customer service. The furthest customer in this scenario, 1,658 miles away. And then some of the statistics here you can see, I've got 9% of my customers are less than 250 miles away. I've got to get up to about, in order to get to 80%, I've got to get over 1,250 miles. And we'll use this as a reference in the future. So let's take a look at how we are going to optimize this. Again, this is the same spreadsheet we just looked at. I'm going to invoke my solver here and show you how to use the tool we just learned how to use in order to be able to optimize this. Very similar to what we just talked about. What is my objective? So it's this cell right here, I-10. It's the total weight times the total distance. Now I'm trying to minimize this, right? I want to minimize my costs. So I'm trying to find the location in the continental United States where I locate my DC to minimize this. What do I have in order to be able to do that? Well, I'm trying to find the DC location. So I want the latitude and the longitude. I want to see where exactly on the map am I going to locate that. And then my constraints, in this particular case, I don't necessarily need to have constraints, but in order to make this a little easier, I've just put a box around the US. So these latitudes are the 52 degrees north, 23 degrees north latitude is about the northern and the southern border of the US. And likewise, minus 65 degrees and minus 127 degrees is the longitude east and west of the United States. That way it knows just to look in, it's not going to look in China or Australia. It only needs to look in the United States. It's going to make it a little easier to find this. You can see on the bottom here, we're not doing simplex method anymore. It's GRG linear. If you recall, there's some geometry in here. There's sines and cosines and whatnot in the solution to try to figure out the distances. So I can no longer use linear programming. So I've got to change this to GRG linear. I'm going to hit solve on this. And bam, that quickly, within less than 2 seconds, it's found my solution. Now we're down to 18.6 million miles, and 878 miles is the average for each pound. So let's look at a summary here. Let's compare the first two. If you recall, the first one, we went 22.8 miles. Now I'm traveling 18.6 million miles. That's 4.2 million miles eliminated, or 18.5%. This is directionally what's going to be your carbon footprint, right? I've just eliminated about 18.5% from my carbon footprint because I've gone a shorter distance. And over here, each mile before went almost 1,000 miles. Now it's going 878. That's 11.9% reduction. So directionally, it's close to a 12% reduction in cost. It's not going to be exact, but this is directionally going to give you some kind of an idea of how you're going to be able to lower your costs by doing this kind of an analysis, right? So again, that's all we did here was to find an alternative solution. What I'll do here is show you quickly on the map. And you can see here, this was where the existing distribution center was in Fort Worth. The new center it found is up here in West Virginia. Okay, so that's where we're going to actually, I apologize, I've jumped ahead of myself. That's the two DC model. For one DC, it's going to be right in Southern Illinois, somewhere a little bit east of St. Louis. Okay, so to move from here to here is a huge savings in cost. So that's the objective here. What we're trying to do is try to figure out a way that we can minimize our costs. So, okay, now we've just figured out how I can optimize this with one location. What if I wanted to do two locations? Very, very similar in nature. That's all I've done here in this model is I've copied my cells H and I, which included my DC location and all of the distances to all the customers, and I've copied it over to K and L. So now I've got the ability to optimize two different locations. It's going to be the same kind of a drill when I put in the solver. Instead of just having H6 and I6, I'm going to optimize also K6 and L6. So these are going to be my changing variables. The other thing I'm going to need to do here is now I'm going to need to assign each one of my customers to the nearest location. So if I look here, customer one was 1,971 miles from DC1. It was only 112 miles from DC2. So of course I'm going to assign that to DC2. It's going to go down this list and do that for every single one of these and assign the customer to the nearest location. And then here is my combined total of both of these. And I've now dropped my total distance traveled to 11 million miles, and I'm down to 448 miles on average for each one of my pounds. So let's come back over here to our summary. So now we've gone from 22.8 million down to 11.6 million. I've reduced my carbon footprint by over half by using two locations that are optimized, right? And I've gone from almost 1,000 miles per pound down to 448. So I've got I've cut more than 50% off my costs. Now, I had to add a second distribution center to do this, and I've got some costs associated with that. So I'd have to do another analysis to see what it would cost me to run a second distribution center. But this is one part of the equation that we can supply to the analysis that says, if just from an operational perspective, a transportation cost, I'm going to cut more than 50% off my operations by doing 2 locations. Likewise, we could go on and on with this. 3 distribution centers, that's all I've done was made another 2 columns, done the same thing. Now I've got to assign the closest DC to 3 locations, but it's the same exact drill we did before. Let's look at our option summary now. Now we've gone through and we've gone from 22.8 million miles to 8.8 million miles. We chopped 14 million miles off. We've 61.2% of our carbon footprint has been eliminated, and we've carved out almost 2/3 of the cost. Now, again, there's 3 DCs here instead of 1, so I've got 2 extra DCs. That part of the analysis needs to be done. And you can see over here for the 2 DC scenario, there's 1 in Southern California and 1 in West Virginia. In the 3 DC scenario, there's still 1 in Southern California, and now the other 2 have moved to Tennessee and New Jersey. But you can see how quickly and easily we've been able to find the optimal location by using this tool. It's very, very quick, and this is extremely helpful. There's commercial grade software out there that I've used in the past in my experience that have cost upwards of $75,000 per license seat per year. And this does the exact same thing. I've tested it and I can assure you it's the same results. Okay, so that's the Greenfield analysis. Let's move on to our next case study, which is going to be network optimization. As we mentioned here, network optimization, we've got a network that's already built, right? So I've got manufacturing plants, I've got distribution centers, I've got whatever I've got, but it already exists and I'm trying to make the best use of it right now. So again, I've made up this was modeled, this is a fake case study. It's after a real case study that I did. If you look at the name, you can probably figure out what the company was that I did it for. But I just put some fake names in there just to kind of save the proprietary data. So in this particular scenario, what we're looking at is a company called Nurse Paprika. They sell soda in the North American market. So they're introducing 2 new products. They've got a banana flavored soft drink and they've got a lemon lime flavored soft drink. And right now, they don't have the ability to make fruit flavored soft drinks. They do work with contract manufacturers. So they've got people that they can use to make this for them. They've got 1 in Boston, Massachusetts. They've got 1 in Toronto up in Canada, and they've got 1 in Monterrey, Mexico. So Nurse Paprika is going to be supplying the ingredients and the packaging, and the contract manufacturer is going to take those things. They're going to bottle it up. They're going to put the labels on it. They're going to put it in another package, either a 12-pack, a 6-pack, whatever configurations requested, and they're going to charge a per case fee. So the question is, what manufacturing plan do I want to use to minimize my costs? I've got 3 options here. Which one of these manufacturers do I want to use? Or is it a combination of 1 or more of these guys? So let's go back to our spreadsheet model and dive in to the meat of this one. Okay, we're there. So here's the basic construct here. So I've got 2 different products, Bananarama and Citrus Fizz. Here are the contract manufacturers, Boston, Mexico, and Toronto. And here's my costs. I've got ingredients, I've got packaging, and then I've got a contract manufacturing fee that I'm going to be charged by each one of these manufacturers. So in total, you can see that to have Bananarama manufactured at $7.43 a case in Boston, $6.43 a case in Mexico, $7.23 a case in Toronto. So down here is going to be my model that I'm going to use to optimize this. And again, this is a summary right here. You've got the product costs for each one of the products that are being made in Boston, Mexico, and Toronto. Each one of these plants has a capacity, right? So Boston can only do 56,250 cases per month. Likewise, Mexico can manufacture 39,000, Toronto 70,000, 72,250. My marketing department rather has told me that I can sell up to 39,500 cases per month of Bananarama and 102,500 cases of Citrus Fizz. So here is my financial model down here. The yellow cells again are the ones that I have that I can change. And again, the things that I have control over here, what manufacturing plan am I going to do? How many cases am I going to assign to Boston, Mexico, and Toronto of each one of these flavors? So let's see, you can see what will happen here if I type in a couple of numbers. So down here is my production totals. So I've made one of each case, 2 total. I've got my production over under shows me in red because I haven't made what I need. I need to make the desired demand, which is 39,500 and 102.5. And then my total cost is down here. This is right now to make one case of each of these, one in Boston and one in Mexico, is going to cost me $13.40. So let's go ahead and open up the solver because we know we're going to use that tool. Again, my objective is to minimize now. So my cost is down here in the green cell E33, which is I've got up here. I'm minimizing cost, so I want to click the minimize radio button. And what is it that I have the availability to change? Well, everything here in the yellow. It's how many is Boston going to make of each one, and Mexico and Toronto likewise. So what are the constraints that I have? Well, we already know, we've been told that in C30 and C31, the production totals, this needs to be now greater than or equal to my total demand, which is in C21 and D21. I know I can sell up to this amount, so I want to make up to that amount. I don't want to make, I can make more than that, but I don't want to make less. So that's why this is now a greater than or equal to constraint. My other constraint is, well, now I know that the total number of units that I've made that's here in E26 through E28, right down here, is the total number of units per month that are manufactured by each one of these plants, cannot be any more than their capacities. I already know Boston can't do more than 56,250. So this number here down here in row 26 for Boston cannot be more than 56,250. Likewise, the other two can't be more than these two numbers. Those are my constraints. So now we're back to a situation where we can use the simplex method. All the connections in here are linear in nature, which is great for us because it's much more easy to use the simplex method. It's quicker. We're going to hit solve and bam, that fast, less than a second and figure this out, right? So we can take a look at this and we can see what this assigned. It says that we used up this total slack is how much capacity is left over. Well, Mexico and Toronto used all of theirs. Boston did not. So what this is telling me is that for some reason, this model does not like Boston. It thinks Boston's too expensive because it immediately went to Toronto and Mexico and signed all the capacity that they had. And then it went to Boston. Let's just take a look and see if that makes any sense from looking at the numbers. Sure. Here's Boston, 743 versus 643 or 723. It's the most expensive, so that makes sense. Likewise on Citrus Fizz, 692 versus 597 or 673. So Boston is the most expensive. So this is a check, a sanity check that actually makes sense. So that's how quick and easy this is to do this. Let's think about what we did here. We just looked at the manufacturing costs, and the only thing, or the thing we have ignored, is any transportation, right? So let's see if we can add another layer onto this analysis and go from there. So what I want to do now is go to the next tab here. Now we're going to say, okay, well, all the things are manufactured in either Boston, Mexico, or Toronto, but they're not going to be shipped out of there. I've got distribution centers for this company in Los Angeles, Dallas, Chicago, and Philadelphia. These places have lots of other products that I make that I can mix with Bananarama and Citrus Fizz to deliver to my customers. So what I need to do now is once this stuff is manufactured in Boston, Mexico, and Toronto, I've got to get it to either LA, Dallas, Chicago, or Philadelphia. So let's take a look and see. We've got a matrix down here. We've gone in and calculated what the distances are. To get from Boston to LA, it's almost 2,600 miles. To get from Toronto to Philadelphia is 336 miles. I've worked with my transportation planning department, and they have told me that the truckload rates to get from Boston to LA, it's $1,586 for a full truckload to move from Boston to LA. To go from Mexico to Chicago, $2,135. There's one more thing I need to do, and that's what kind of capacity do I have on a truck? I know from the way that I can, my pallet positioning and how many pallets I can put on a truck. I can get 2,400 cases of each one of these on a truck. So if I divide this 1586 by 2,400, what that tells me is to move product from Boston to LA, it's 66 cents per case. To move from Mexico to Chicago, it's 89 cents per case. It's important for me to get this on a per case basis because everything else is already on a per case basis. So in order to compare apples to apples, I want to do that. So now I've opened my matrix up a little bit. Now, instead of just having Boston, Mexico, and Toronto, I've got to get this to these different locations. So now, if I looked at Boston, it was $7.43 to manufacture Bananarama in Boston and then 66 cents to deliver it to LA. Those two numbers together equal $8.09, right? And likewise, the rest, sorry about that, the rest of this matrix is the total landed cost, right? Not just transport, not just manufacturing, but what does it cost to make this product in Boston and get it shipped to each and every one of these locations. Now, for simplicity purposes, we've assumed down here that because we've got 4 locations, that each one is going to take 25% of the demand. So 39,500 divided by 4 gives me 25% in, or excuse me, 25% in each one. So I need 9,875 cases each one of these locations for Bananarama, 25,625 in each one of these locations of Citrus Fizz. So now this has got a lot more changing variables, right? It's not only how much I'm going to make, it's how much am I going to make in each location and send to which one of these distribution centers. Up here in the purple, this is going to be my total landed cost for the solution. I've got nothing in here right now, but if I put 1 in here, that's going to be, I don't have the cents on here, but it's going to be basically the 809 to ship 1 from Boston to LA. So we know exactly what we want to do here again. We are going to hit our solver, pull up that, and same drill here, right? So what's my objective? Well, my total cost is right here in S13. That's what I want to click in here. That's my objective cell. This is the cell that's going to be changing as I change all the numbers down here in yellow. I'm going to minimize. Again, this is a cost structure, so I want to minimize my costs. By changing which variables? Well, everything in yellow. I want to come up with a number in every single one of these. It could be 0. I may not use any of these, but some of them are going to be non-zero. And then what are my constraints? It's the same drill again. Here I've got L23 through S23. So that's the units that I've shipped. So the units that I've shipped to each of LA, Dallas, Chicago, and Philadelphia needs to be at least greater than or equal to the demand that I've got for cases in each location. So that's one of my constraints. The second constraint I'm going to have, it's just like I had before, right? Each one of these manufacturing plants, Boston, Toronto, and Mexico, they all have a certain capacity, and I can't go above that. So my other constraint is that these 3 cells here, the actual production cases I've got, which is just the sum total of everything along the row for Boston, Mexico, and Toronto, these 3 numbers cannot be greater than this. So that's why I've got a less than or equal to in that constraint. Again, this is all going to be linear in nature. So I've got my simplex algorithm. I'm going to hit solve, and bam, again, in under a second, it comes up with the solution. So what are we finding here? Again, it doesn't really like Boston that much. It loaded up on Toronto. Actually, no, I apologize. It's backwards. So Boston is actually now preferred. There's no slack in Boston. So it's before in the last scenario we had, Boston was kind of minimized because it was so expensive. But now, because we've added transportation costs in here, and because of the proximity of Boston to both Philadelphia and Chicago, presumably, it says, hey, I kind of like Boston more than I like Toronto now. Mexico, it still has used up all of the production capacity in Mexico, but I've flipped now from Toronto to Boston. Makes sense? So again, this is, depending on in supply chain, these are the kinds of questions that need to be answered all the time. When I was at Dr. Pepper, this was a daily event. We were constantly trying to figure out, hey, depending on where the demand's going to be, or hey, I've got a plant that's going down over here that made Dr. Pepper, and I've got to distribute this out somewhere else. But based on what I've got left, what's the least expensive way for me to do this? So this is the kind of, if you're in supply chain, you really need to familiarize yourself with these kinds of analyses, because these things happen all the time. And hopefully what I've been able to show here, it's fairly easy to do this in Excel. So we've got a couple minutes. Let me show you just one more layer on top of this. So far, we've looked at a scenario where we've done contract manufacturing on all this stuff. But what if we said, hey, we're paying a pretty hefty price, right, to have this. I'm paying a $3 or whatever it was. I've got $3.22 a case, $2.29 a case. There's not a ton of profit in the soda industry. What if I wanted to make this stuff by myself? Could I do that? Would I do it? And what would it look like? Okay, well, it just so happens that each one of these distribution centers is also a manufacturing facility, right? So what we've got here now is we can add production capacity to any one of these manufacturing facilities. And then now we've got to take a look at, okay, well, now I may have to deliver product from one of my own internal distribution centers, manufacturing facilities, we can call it, to another distribution center. So obviously to get to LA is 0. If I make something in LA, it's already where it needs to be. So I'm going to have a 0 transportation cost. Anything on the diagonal here is going to be a 0 because it's just delivering things to themselves. But we went through the same drill here, worked with our transportation people to get from Dallas to LA. A truckload is $1,686. I can put 2,400 cases on a truck still. So this is my per case value. And then my transportation cost, this is my transportation cost per case just internally. Here's my old transportation costs from Boston to LA. And what I'm going to come up here is going to make one giant matrix now that's got all of my external facilities as well as internal facilities, because right now I don't know what I'm going to want to do, right? I need to leave it open that I may still want to use my contract manufacturers, and I could use any and all of my internal locations. There's one more thing I need to consider, and that is, what is this going to cost me, right? So I've worked with my engineering team, and we've come up with, in order to put this kind of capability in Los Angeles, it's going to cost me $4.25 million. And that's going to give me the capacity to manufacture 35,000 cases per month. They're telling me this is a 5-year useful life on this equipment. So that amortizes out to $70,833 per month, or about $2 a case. If I divide the 70,000 by 35,000, it gives me $2 a case. So likewise, It cost me 3.75 mil in Dallas, 3.925 in Chicago, and 5.175 in Philadelphia. So I'm taking these numbers, the 70,000, all the monthly amortizations, and I've put it up here. And the question that you may be asking is, hey, I already put this down to the per case level. Why wouldn't I just add a per case? Well, everything else is in a per case. All the financials are in a per case. Why wouldn't I just add $2.02 here? And the reason is, for a contract manufacturer, I can ask them to make one case. I can ask them to make two cases, 50 cases, whatever. If I spend $4.25 million, that money's spent in LA. Whether I decide to use that or not use it, I'm going to spend that money. So this is kind of an all or nothing situation, right? I can't just partially use this. If I spend the money to put it in there, I'm in for a penny, in for a pound. So what I've got to do now is I've got to add an extra constraint on here. So I've got this column S, which says build question mark. All these are in pink now because I've added another variable. It's called a binary variable. And what you can do is look down here and you can see this is going to be my part that I'm going to be changing all these numbers down here in pink. These are the ones that I can change in order to optimize this. You can see right now, here's my manufacturing capacity. The ones for Boston, Mexico, and Toronto are in there already, but I've got nothing for LA. That's because these are all zero, right? But if I came up here and I said, oh, I do want to build the one in LA, now I've got 35, just like it says down here, I've got a 35,000 case per month manufacturing capability. So what's going to happen is all these numbers in pink down here are going to change to determine how many cases should be produced at each place to go to which place. And then all of these four cells here will vacillate back and forth between 1 and 0, depending on how the thing's optimized to what needs to be made. So let's just jump right into the solver, and we can see it's a very similar setup, same as we've looked at before. Now my purple down here is my total landed cost. That's Q29. I'm minimizing. What can I change? So now I've got two different areas of the spreadsheet that I can change. I've got J33 to Q39, which is everything down here in the pink. And then I've got S24 to 27. I can change all these as well, okay? What are my constraints? It's the same constraints I had before. My demand has got to be in each location. Down here, the unit shipped has got to be greater than the demand in each one of the locations. My production in each facility can be no more than the manufacturing capacity. And now I've added one more constraint on this, and that's this S24 to S27 is binary. What that's telling it is that, hey, this can only be a 0 and 1. It can't be anything. I can't do a half of, I can't do a quarter of a production plant. I can make it or I can't make it. Those are my options, right? So now, again, we're using the simplex algorithm. I'm going to hit solve. Bang. Again, it's very, very quick. And what this has told me is, okay, it wants to use 3 different internal locations. It wants to build LA, Chicago, and Philadelphia. It doesn't like Dallas for some reason. So the thing is, the other thing we haven't considered here is, what is this going to cost, right? Or we've added 3 new capabilities to all of our plants. So let me show you quickly how to add a new constraint. Let's say that somebody came up and said, hey, I'm going to make this equal to the sum of these 4. So this is telling me I've got 3 plants. And then over here is going to be a cell that I use as a constraint. I'm going to say, put a 2 there. And I'll show you what I'm going to do here in a second. I'm going to pull up my solver. Everything else is the same. I'm going to add one constraint. So I'm going to come over here to the side. I'm going to say add. Okay, this opens up my second window. What's my cell reference? I'm going to say this cell here, which is the sum total of everything I'm going to build. needs to be less than, or it defaults to less than or equal to. You've got less than or equal to, greater than or equal to, integer, binary, etc. This needs to be less than or equal to this one right here. That number can't change. 2 is a constant. And then I'm going to go ahead, I'm going to solve this again. Bam, it already figured it out. It says, okay, if you could only let me do 2, then I'm going to do LA in Philadelphia. Hey, what if I said, hey, I could only afford to do 1 of these? No problem. I just change that to 1. I come back up here to my solver. I've already got the constraint in there. I solve it again. Bam, it's done. Now, if I only could do 1, it really likes LA. Okay, so you can see how you can very quickly and easily change these types of variables. These models are not that difficult to build, as you can see right here. And in my experience, which has been over a number of years, these things are extremely useful. Like I said, when I was at Dr. Pepper, this was a daily event. We were constantly trying to figure out. Now, Dr. Pepper was a very sophisticated supply chain, right? There were 11 manufacturing plants internally. I can't remember, 5 or 6 different contract manufacturers. We had 3 gigantic regional distribution centers. There were 146 smaller distribution centers. So, there's a lot of moving parts going on there. And, occasionally we'd say, hey, you got to shut down for maintenance one of these plants. Okay, now how do I work my way around that? And so we'd be working this kind of stuff all the time, but you can really quickly and easily do this and come up with your answer. So I hope these 2 case studies have given you some kind of an idea of what this tool can do. So before I open it up for questions, just a few parting thoughts, right? So I mentioned earlier, I've worked for a couple different companies now. Dr. Pepper was one of them and Galderma was another. We had this expensive software. I won't throw anybody under the bus because the software is actually quite good, right? But we were paying $75,000 per licensee per year. Now, is it different than Excel? Internally, the algorithms it uses are the same. It's got a lot more bells and whistles, right? There's all kinds of graphing capabilities, and you can do all kinds of different things with it. So I'm not going to throw them under the bus and say that it's not useful. But my point here is that we were able to, when we figured out, when I went when we first started using it at Dr. Pepper, I went to the training at the headquarters for this company. And on day 1, they were telling us, yeah, we use the simplest algorithm. I'm like, oh my goodness, I happen to know a lot about the solver, and I know solver uses the simplex algorithm. Let me see if I can actually figure out how to do this. So we got back from this training, and I made it my mission to try to learn how to do this. And I created these models that I just shared with you. And one of the first things I did after I created it was I worked with one of my colleagues and I said, hey, here's a real life situation we've got. Here's a problem that's been given to us. We're going to both use the same input data. I want you to use the expensive tool that we just learned how to do. I'm going to do it in Excel, and we're going to come back and see what the solution is. We went away for a few days, came back when we both finished and looked at the solutions. And I mean, to the penny, to the pound, to the mile, every single thing about the solution was exactly the same. So I know that this provides the exact same answer that you're going to get using this very expensive software. The thing you're not going to get is all of the fancy graphics. I think one of the things that I think is a benefit to using Excel is when you have to create the model, you're going to understand this intimately, right? You're going to know what happens. What are the different levers you can have? What are the things, like when we looked at the thing at the end of the run, I said, oh, it must not like Boston for some reason. Let's go up there. Yep, sure enough. So you start to understand these things deeply, right? Whereas if you're using a black box piece of software, you're just putting numbers in and getting numbers out. When you're involved in the development of the model, you really have a good understanding of what's happening. So just, kind of in summary, I really feel like if you master this skill, it's going to really up your game. It's going to make you so much more valuable. If you're an employee in a company, you're going to be much more valuable to your employer, which is going to make it easier for you to get raises, bonuses, promotions, or new jobs outside the company. If you're a consultant, it's going to give you a broader range of things that you can offer to your clients, and it's going to be able to help you to serve your clients so much better. I mean, I really think that this is something that anybody that wants to be labeled as a really, really good analyst, be it supply chain or any other function within the company, by learning this Excel solver is going to take your capabilities to the next level. So that's all that I had to share specifically tonight. If there's any questions that anybody has, I'd be happy to answer any questions.